It's my pleasure to introduce Professor Masaki Oshikawa of the University of Tokyo for this talk as part of the TSVP thematic program on generalized symmetries. So Professor Oshikawa was born and educated in Japan. He first went to the University of Tokyo, I think, in 1986 and graduated from Komaba to the Department of Physics, where he wrote his bachelor's thesis, and then a master's thesis with Professor Izuyama. And there he moved to the legendary Institute for Solid State Physics, which was then in Roppongi, an exciting part of Tokyo. And in 1995, defended a PhD on hidden symmetry and phase transitions in quantum spin chains with general integer spin, which was supervised by Professor Komoto. And if I'm reading this right, you'd already been recruited as a research associate by Naoto Nagaosu at that point. So this is kind of assistant professor status position before you've technically finished your PhD. And from there, Masaki went to a postdoc in the University of British Columbia, working with Ian Affleck, where they co-authored a series of very beautiful papers on spin chains that I can actually remember reading in archive format when the archive was CONMAT and still relatively new when I was a PhD student. So that these papers made an impression on me at the time, and they made an impression on quite a lot of people. So for that work, Masaki won the 2000 and check date, I think it's 7 Kubo Prize for physics, and then some further prizes, I think, from the ESR community. There would be more prizes later. From the University of British Columbia, he went to Tokyo Institute of Technology, recently renamed, and he was faculty there for a number of years before moving back to the University of Tokyo, and indeed moving back to ISSP, where he's been since 2006, that's right. So Masaki is known for very creative and original and somewhat deep thinking about quantum systems, not exclusively, but often in one dimension. He managed to get his name added on to the Lieb-Schultz-Mattis theorem, which is everybody's favorite theorem in one dimension, and now associated with Masaki as well. And since I'm summarizing his accomplishments, I will mention one other paper which had, I guess, a huge impact, which was the determination of an SPT through entanglement spectra. So this paper has, it's heading for 2000 citations and was included in the scientific material related to the Nobel Prize in, 2015, when Haldane and Thalus won. So Masaki is distinguished. He's written what I consider respectably few papers, so not that many more than 100, but many of them have many citations and a big impact. And he's very, very well qualified to talk about the subject of indistinguishability and statistics of quantum particles. I'm looking forward to hearing about that today.
Okay, thank you. Thank you, Nick, for kind introduction. And I'd like to, also I'm the participant to this TSVP program on general symmetries in quantum matter. So I'd like to thank the organizers, especially Danny and all the staffs at OIST, to make the wonderful program symposium to happen. And also I'm enjoying staying in Okinawa, cycling around with my bicycle, and also swimming in several beaches. Okay, so I was asked to give a general talk. So actually my talk today is really based on my general public talk I gave in a few times in the past. So I aimed this talk, at least the first part was aimed for high school students or even elementary school students. So I see many of physics colleagues. So for you guys, maybe this is trivial, but still I hope this is enjoyable. Okay, so yeah, because this is the public talk, I start from what makes up matter. We ourselves are made of some material, and there are many materials, including chalks, blackboard, and everything. But for example, just water in glass. So this is basically made up of water molecules. There are a huge number of molecules inside, as you know. And molecules consist of, this water molecule consists of 2 hydrogen atoms and then 1 oxygen atom. And the hydrogen atom is made up of 1 proton and electron. So these are microscopic particles. And especially the electrons is supposed to be elementary particle. And we often, draw illustration for atoms and electrons like this. But what are really those particles? And when we draw pictures like this, we are kind of assuming that these particles are something like small balls or grains. But of course, the size is very, very tiny. But of course, the size is very different from basketball or baseball or soccer ball. But is that the only difference between the balls we are familiar and those microscopic particles? That is my first question today. And one interesting thing is that we or human beings or scientists reach the idea of atoms without too much advanced experimental techniques. So, for example, famously back in 1905, Einstein wrote one of the very influential paper on Brownian motion. And if you put a small particle in the water, like a pollen, and then pollen moves randomly, and from that, you can infer that actually water molecules are doing random motion. And then water molecule hit those pollen, and then pollen makes also random walk. And from that kind of many indirect evidences, people could conclude that the material should be made up of atoms. Although back in that time, you couldn't really see the atoms directly. But these days, we have better experimental equipment. So for example, this is actually a picture of atom. So this is a silicon surface observed by atomic force microscope. I borrowed this picture from my colleague Hasegawa-san in ISSP. And we see many things which looks like a ball. And each ball or ball-like object actually is indeed a single atom of silicon. So in this way, these days, you can see the atoms, and they do look like balls. Okay. So it's tempting to think like those microscopic particles are really like balls, although size is much smaller. But yeah, my question is, are these atoms or electrons, are they really like balls? So to illustrate this point, I asked my assistant, who is my daughter, although, okay, this is many years ago, so she's now grown up. But anyway, so she came up with 2 balls. And my question is, can you distinguish these 2 balls? And well, so she has 2 balls, which looks same. Yeah, because I bought a package of balls, which contains, same size of balls, several. So it appears that you cannot distinguish these balls. But of course, it's not really true, because, yeah, actually on one of the balls, on the back side, she wrote her own name, and on the other ball, there is nothing. So you can distinguish these 2 balls by just writing a name, or you have secret code, whatever. So in that sense, balls, as we know, are distinguishable. So even when these two balls look identical, almost the same, look exactly the same, but these balls, a macroscopic object, can be distinguished, at least in principle. For example, by writing your name secretly on the backside, or many other ways to distinguish these balls. But the important point is that these balls are distinguishable, at least in principle. But the point I want to make is that there are really identical particles in microscopic world, like atoms and electrons, which you cannot really distinguish, even in principle. That's a huge difference from both we know. So you draw similar picture, like a balls for these particles, but the huge difference is that you cannot really distinguish two electrons. So in other words, you cannot secretly write your own name on the back of electron or atom or whatever. So that's a important point. So this is, well, so philosophically interesting, but not just philosophical interest, but this is really important because as I'm going to demonstrate, this difference will lead to several dramatic, interesting physical phenomena. So to illustrate a point, I want to discuss maybe simplest example. And so in our daily life, we buy many things. And these days, you can buy many things using Suica or PayPay or credit card and so on. But historically, we have been using these kind of devices, bills and coins. And in case of coins, usually each coin has two sides with different designs. So for example, this is a 100 Japanese yen coin. Probably this is the head, omote, and this is tail, backside, although maybe I'm wrong. Anyway, this 100 yen coin has two sides, head and tail. And this has a practical application. Because this is one familiar application of this coin. So when you start a soccer game, he drops a coin, but in this case, coin stands up exactly, so you couldn't determine which side kicks first. But usually if you throw coin, then head or tail comes up, so you can decide which team kick ball first. Anyway, so this is a coin tossing. And so this coin tossing is very simple problem. So it appears often in high school or college mathematics. And this is one common question in maybe high school probability, high school mathematics probability section. So usually we assume that when you flip the coin, when you toss a coin, the head or tail comes out with probability 50% or 1/2. Although in real coin, the design is different, so weight is slightly different. So maybe not exactly 1/2, but usually we assume that post 1/2, and probably it's close to 1/2. Then if you toss one coin, then it's simple, 50% head, 50% tail. Then our next question is, if you have two coins and you toss these two coins at the same time, then what is the probability of you having two coins both showing the head? That's the question. So this is an elementary question. Probably, of course, you guys know the answer, but still this is kind of interesting because this shows a common pitfall in probability theory. Because often students might answer like, okay, so what are possible cases? So if you have two coins, there are three possible outcomes. So one is you have two heads, and another is you have one head and one tail. And finally, it's possible to have two tails. Okay, so there are three possible outcomes. Then, okay, so head and tail comes out with same probability. Then these three outcomes should occur at the same probability. And if that is the case, then these two heads should occur with probability 1/3. Okay, so this sounds reasonable to some extent, but of course, you know that this is wrong. Okay, but it's interesting to think deeply why this is wrong, because to some extent, this is makes sense. This argument does make sense. So what I want to emphasize is that, of course, the previous answer was wrong, but that was wrong because of some fundamental assumption. That is, this is a correct answer. So actually, there's a first coin and second coin, and each coin can show head or tail. So if you make a table, actually there are 4 possible outcomes. So head-head or head-tail or tail-head or tail-tail. So and there are 4 possible outcomes, and every outcome should occur with the same probability if the head and tail will appear at the same probability. So if you look at this table, there are 4 outcomes with equal probability, and if you want to discuss the probability of getting this head-head, this is one of the 4 possible outcomes. So the answer, that is probability of having this head-head, should be 1/4, 25%. And of course, this is a correct answer. So if in high school mathematics, if you write the answer like in previous slide, you get wrong. And if you answer like this, well, you get the perfect score. But as you might have noticed, so this correct answer actually relies on the fundamental assumption. That is, we need to assume that these 2 coins, even when they look very similar, they are distinguishable, at least in principle. Now, of course, in real coin, there are 2 different positions, so they are indeed distinguishable. But I'm thinking about very idealized situation where coins have only 2 degrees of freedom, head or tail. So in that case, you need to distinguish these 2 cases to derive the correct answer. And this fundamental assumption that 2 coins can be distinguished is basically called classical statistics. So quantum statistics can be different. That's my point. So if we ask hypothetical question that if my coins are really indistinguishable, then there are indeed 3 possible outcomes: 2 heads, 1 head and 1 tail, and 2 tails, because you cannot distinguish head tail and tail head. And these 3 outcomes should happen with equal probability. So this is nothing but a wrong answer I introduced earlier. But this wrong answer becomes correct if 2 coins were really indistinguishable. And this is what we call Bose statistics, or Bose-Einstein statistics, because this kind of mysterious statistics do happen in microscopic world. And this statistics is named after 2 physicists, Bose and Einstein. And Bose was the Indian, Satyendra and Bose, S.N. Bose, and also famous Einstein, everyone knows. And this was proposed in 1924. And the story how these 2 physicists are associated to this concept is kind of interesting, because he was in India and Einstein was in Germany at that time, and that was more than 100 years ago. So you couldn't fly easily with airplane. So actually, I went to Calcutta, where Bose was born and grew up. And now they have built SN Bose Institute, Satyendra Nath Bose National Center for Basic Sciences, some new institute, well, no, not new now, but yeah, after Bose, they founded this research center in honor of this Bose. And I went there with my bike. And on their campus, they have Bose archive. So they have, yeah, they have some collection of mementos about this SN Bose. So I went there, and they keep several interesting materials, including this letter. Of course, this is a copy, but this is a copy of the letter from Einstein to Bose. Actually, Bose wrote to Einstein earlier, so he explained his idea about new concept at that time. That is nothing but Bose-Einstein statistics. But Bose wrote this idea to Einstein as a personal letter. Then Einstein received this letter. And at that time, Einstein was already super famous, I think, after special and general relativity. And probably Bose was, not known in Western world. But still, Einstein read the letter, and he was very impressed by this idea. So this is his answer. So actually, Einstein translated Bose's letter into German, and he published this paper in Zeitschrift for Pure Physics, because Germany was, the dominant in physics at that time. This Zeitschrift was a leading journal in physics. So he took liberty of, translating his Bose theory to German and publishing this Zeitschrift. And he had some criticism to Bose, but anyway, so he was very impressed. So yeah, this is a original paper published in Zeitschrift Physics. So yeah, received in July 1924, but received, I think, from Einstein by the journal. And this German text was due to Einstein. And well, yeah, so Einstein was, of course, a very fair person. So he put just a name of Bose as an author. And his name, Einstein's name, appears only as a translator. But yeah, he also made a remark as a translator. But anyway, but one funny thing is that Bose is very popular family name in India. So you probably know the Bose speaker and also Bose who contributed to independence movement and so on. So many famous Bose, but probably Einstein didn't care what was his first name. So he just wrote from Bose. Yeah. Anyway, so yeah, so that was history of Bose-Einstein statistics. And as I said, if you toss two coins obeying the Bose-Einstein statistics, then probability of having two heads should be 1/4 in usual classical statistics, but in Bose statistics, it's 1/3. So that implies some interesting stuff because, okay, as I emphasize, of course, you cannot really distinguish first coin from second coin. But for the sake of argument, temporarily, I pretend like you can distinguish two coins. And you toss two coins sequentially. So suppose that you, after tossing the first coin, this first coin showed head. Then you ask a question, what is the probability of second coin also shows a head after tossing? So, of course, when you toss only one coin, first coin, having the head occurs with probability 1/2. But in Bose-Einstein statistics, after throwing the second coin, the probability of having both heads is actually 1/3. In contrast to classical 1/4, which means that assuming that the first coin already showed head, probability of having second coin also showing the head must be 2/3 in both statistics, because that 1/2 times 2/3 is 1/3. Whereas in classical statistics, 1/2 times 1/2 is 1/4. So this is an important point. So this implies that if the first coin already takes out some state, like a head, then if you toss the second coin is more likely to show the same state, head, if the first coin was already showing a head. So this implies that in both statistics, these coins or microscopic particles or whatever tend to take the same state compared to the usual classical statistics. And that leads to a very interesting phenomena. I want to, again, illustrate with some coin example. So, of course, this is a fictitious example. But as I said initially in the beginning, we often idealize the coin as completely symmetric, and the head and tail shows with probability exactly 50%, 1/2. But the real coin may be asymmetric. So let's say head will show with probability 50.1%. That means that you will get the tail with probability 49.9% if you toss single coin. So for this kind of asymmetric coin, what happens if you toss two coins? Both coins have this probability distribution. So in classical statistics, you draw the same table, head, and tail, and head, tail, head, tail, and tail, tail. And you just multiply 0.501 times 0.501. Then probability of having both heads is like a 25.1001%, and so on. So this you can easily feel. And of course, total should be 100%. So this is another maybe high school mathematics problem. But then what you have many more coins with the same probability distribution and toss many coins. So if you toss 10 coins, then among 10 coins, you can have 0 to 10 heads. And this is a number distribution with a probability. And so after tossing 10 coins, you should have a probability distribution like this. And if you increase the number of coins, for example, if you toss 100 coins, then probability distribution looks like this. Maximum 100 heads and minimum 0 heads. But in principle, you can have any number of heads. And if you toss 1,000 coins, probability distribution looks like this. So this is a familiar example of the law of large numbers, or the central limit theorem. So this probability distribution asymptotically approaches the Gaussian normal distribution. And this width is only proportional to the square root of this number of coins. So relative to the entire range, this probability distribution becomes narrower and narrower. So as you increase the number of coins, you are almost sure that basically 50.1% of all the coins will show the head, and the 49.9% of all the coins should show the tail. And there is small random fluctuation around this average. Yeah, so for 10,000 coins, it looks really like a sharp. So this is a consequence of classical statistics we are familiar with. And this is, again, maybe a good exercise in high school or college mathematics, elementary probabilities. But if you have coins which obey both statistics, then the situation is very different. So now, if you throw 10 coins, then, okay, so actually, if head and tail occurs at the same probability, then there are 11 possible outcomes, because the number of heads can be 0, 1, 2, 3, 4, up to 10. So there are 11 possible outcomes, and all the outcomes should occur at equal probability. So for symmetric coin, the probability is all the same, the flat distribution. So this is already different from classical statistics, because there is no, the distribution is already very broad. But because of the slight asymmetry, the having, for example, 10 head, this probability is slightly larger than other outcomes. But because this asymmetry was very small, like 50.1 versus 49.9, this difference is not very visible. But now I want to increase the number of coins. Again, obeying the both Einstein statistics, of course, very hypothetical coin. But if you toss 100 coins, obeying this both Einstein statistics, then again, there are 101 possible outcomes. But now you see clear gradient. That is probability of having 100 coins or head is visibly larger than other possibilities. And now I increase the number of coins, like 1,000 coins. Then, yeah, the distribution is even more skewed. And if I toss 10,000 coins, then probability distribution is almost concentrated in this side. Means that even though each coin is slightly asymmetric, 50.1% head and 49.9% tail, if you toss 10,000 coins, then you almost always have nearly 10,000 coins showing heads. So the reason behind this phenomenon is that each coin was slightly asymmetric. Then this is kind of enhanced by this both Einstein statistics effect, because as I mentioned earlier, in both Einstein statistics, if other guys are already taking some state, then added particles tend to occupy the same state. So this slight asymmetry is gradually enhanced as you increase the number of coins. So this is the effect of both Einstein statistics. And of course, this is a hypothetical example. But so this leads to a very important physical phenomenon, that is Bose-Einstein condensation. So as I mentioned, Bose proposed his idea of Bose statistics in his personal letter to Einstein in 1924. And Einstein was immediately interviewed, and he even translated Bose theory into German and published a paper. But after that, Einstein kept thinking about this statistics. And then he actually came to the conclusion that if atoms are obeying this Bose statistics, then you can have a condensation of macroscopic number of atoms at sufficiently low temperature. And this is called Bose-Einstein condensation. And as I mentioned, very hand-waving explanation of this phenomena is particles obeying the Bose-Einstein statistics tend to occupy the same state, even if the initial asymmetry is small. So it's like a birds of feather flock together. So there are many real physical systems which are related to this concept of Bose-Einstein condensation. Actually, superfluidity of liquid helium may be regarded as a Bose-Einstein condensation of helium atoms. And the superconductivity is also, in some sense, superfluidity, also related to Bose-Einstein condensation. But these systems are far from ideal case of Bose-Einstein condensation. But relatively recently, Bose-Einstein condensation of almost ideal atomic gas, which was originally discussed by Einstein around that time, was realized in experimental lab. So this is, okay, by now it's like 30 years ago. But so in principle, any atom which obey this Bose-Einstein statistics can show this Bose-Einstein condensation. But the problem is that you need to cool down the system to very low temperature. And there was a progress in so-called laser cooling techniques, which got the Nobel Prize in Physics in '97. And using this technique, people succeeded in cool down the gas of atoms to very, very low temperature. So this is one of the first report by University of Colorado group in '95. That was 70 years after the original prediction by Einstein. So at relatively high temperature, you have, so this is a real space image, but at high temperature, you have some normal distribution atoms. But as you cool down the system in temperature, in absolute temperature, 2 in 10 million, 5 in 100 million, very, very low temperature, you suddenly see the spike of atomic distribution near the center. So this corresponds to condensation of macroscopic or many number of atoms into the same ground state. So this is a clear observation of the Bose-Einstein condensation of almost ideal bosonic atoms. Okay, so one of the points I wanted to make is that this Bose-Einstein condensation is a consequence of Bose-Einstein statistics, how to count the number of possible outcomes, and it's very different from classical statistics. But once you admit that the particles are really indistinguishable, then this Bose-Einstein statistics and also Bose-Einstein condensation naturally follows. But then I want to come back to this question. So in the case of usual Bose, you can always distinguish in one way or another. But for this concept of Bose-Einstein statistics or Bose-Einstein condensation, it's necessary that those particles are really indistinguishable, even in principle. That's a very strong statement, and in some sense very mysterious, because this is so unfamiliar from our daily lives. So maybe we can ask why it's possible that you can not even in principle distinguish identical particles. So that's my next question. Of course, one answer is that nature just works like that. Because if you do this experiment, cool down the atomic gas to ultra low temperature, you do observe Bose-Einstein condensation in perfect accord with theory. So in that sense, it's already experimentally shown. So you have to accept. So this is how science, physics works. Of course, that's true. At least one aspect of science, we need to accept the reality, even if that contradicts with your initial belief or your preference or whatever. But still, you might ask why this is still possible. And to this kind of question, actually, Shinichiro Tomonaga gave a kind of interesting answer. So probably maybe, well, physics colleagues should know Tomonaga, but yeah, he got a Nobel Prize in Physics in '65 for the work on realization of quantum electrodynamics. Same time with Feynman and Schwinger. But in our field, condensed matter physics, maybe these days, he's maybe better known by his work on so-called Tomonaga-Rattinger lead. Actually, his work was much earlier than Rattinger and also more correct, I have to say. But another curiosity is that actually he was a classmate of Hideki Yukawa. Yukawa was the first Nobel laureate in Japan, and Tomonaga was second, I believe. And they were actually classmates. And yeah, they were discussing physics since their student days. Anyway, so he was clearly great physicist. But another aspect I like about him I like is that he wrote several books, which was often outcome of his own struggle in physics or his own questioning physics and so on. Of course, most of the books he wrote was in Japanese, but several were translated. So yeah, I suggest reading his book. They are really nice. Anyway, so in one of the books, maybe this is not translated in English, I'm not so sure, but anyway, so in one of the books, he actually addresses this question: why we have those identical particles you cannot distinguish even in principle. So I want to introduce what was his kind of answer or maybe interpretation. So these days electronic displays are everywhere, like my laptop screen, iPhone, station, airport, everywhere. So somehow I took this in metro inside. This is inside the metro train in Tashkent, capital of Uzbekistan. But anyway, so yeah, we see this kind of screen almost every day these days. But these days, these screens are so fine that you often forget how this works because it looks almost natural. But back when I was a student or kid, those displays were more primitive, and of course, primitive was not nice. But on the other hand, primitive, apparatus mechanism, it's easier to understand how it works. So I will show more primitive version of this kind of electronic display. So this is inside some Japanese train. So it shows some message. Okay. So we often see this kind of display. But this is similar to more refined display. But with this, it's easier to understand how it works because there are dots, and every dot is like a LED lamp. So usually it's turned off, but when you want to show these characters or numbers, you just turn on this LED light to orange or green or whatever. So actually this is somehow Tomonaga's answer to our question. Because so as I mentioned in the beginning, traditionally you try to understand the particles as some kind of small balls or grains. So these balls are flying around in empty space, maybe colliding with each other or something. But in modern physics or contemporary physics, somehow the idea of vacuum and particle have evolved and became rather different. So in technical term, the contemporary idea of this, the physics idea on this vacuum and particles are called quantum field theory. And according to quantum field theory, so traditional vacuum is nothing, just empty. But in modern point of view, quantum field theory, vacuum is actually far from nothing. It's very complicated thing filling our space. And so this is something like this electronic display or electronic signboard. So it has many mechanisms already included. So you can excite this quantum field in space, which is something like you turn light on this electronic display. And then this turned on dot of the display basically corresponds to the particle, microscopic particle, like electrons and so on. So actually modern physics point of view of vacuum and particles is more like this, rather than some ball in an empty space. So if you accept this kind of picture, then as a natural consequence, actually particles are now indistinguishable. Because if you imagine LED board, lot of small LED lights on the board, and initially it was all turned off, But now you turn on this light and this light, and these two are two particles. Then you move this particle, but moving this particle actually means that turning off the light and just turn on the next light. If you repeat, it looks like these particles are moving. Then you can make these two particles collide and let's say repulse. But after this repulsion, can you say whether this particle is bounced back by collision or they just went through the other particle? And you cannot answer because now my particle is just a status of this LED, electronic signboard. So you cannot say whether this light on originally came from this side or this side. It's just a status of the light. And in fact, in modern quantum field theory language, particle is really like light turned on. So of course, this is very hand-waving, but if you study quantum field theory, now concept of particle is really something like that. Then as a natural consequence, you cannot really distinguish the particle. Okay. So then it also, this point of view also has other applications. So I'm changing the subject a little bit, but now I consider magnet. So we are familiar with magnet. Like in elementary school, we played with this kind of magnet. So one side is no N and the other side is S. And there is a magnetic field between these two sides. And if you cut this magnet into half, then both halves of this magnet is again a magnet, like this, as you know. And you can keep cutting this magnet into half, and every fragment is again a magnet. So it looks like a endless process, but of course it isn't. Because eventually this magnetism of magnet comes from electron. So because we draw electron atoms like this, but actually this is not really faithful representation of real electron atoms. But anyway, so we have electron, but each electron has a small magnetic moment. So each electron is basically a tiny magnet, so to speak. So it is this electron, so we call this spin, electron spin. And this electron spin is the origin of the magnetism of the magnet we are familiar. So so any material, including my body or water in a glass or blackboard, have huge number of electrons. So in principle, they can all be magnet, but most of the materials are not magnetic, non-magnetic. Because usually electron spins cancel with each other. That means if some of the electron spins pointing up, some others are pointing down, and the net magnetic moment is almost zero in most of the material. But if for some reason you can align the direction of an electron spin, then you can have a magnet. But why that happens is another interesting story, but I don't go into that part for today. But anyway, so now we consider the how to align electron spins. So for example, in initial state, all electron spins are pointing down, then overall magnetization looks like this. Then I want to control the magnitude of this overall magnetization, to which you can, for that, you can apply the magnetic field. Then, so as you increase the magnetic field, you can flip some of the spins. For example, this guy or this guy. So this guy, is flipped. So as you increase the strength of the magnetic field, you can flip more spins. Then overall magnetization becomes smaller and smaller. And finally, if 50% of electron spins is pointing up and the other 50% pointing down, then overall magnetization is zero. In this way, by applying magnetic field, you can control the overall magnetization of the electron spin in some given material. So, so we are interested in how this flipped spin, electron spin, can affect the magnetic property of the material. Okay, so this is a now old experiment, but still let me introduce this to you. So there are many materials, but for many years it was difficult to do this kind of experiment in ideal conditions. But my old colleague in Tokyo Tech, Tanaka Sensei's group, found this material. And this actual photo of the crystal. And this gave us almost ideal playground to apply the magnetic field and flip this electron spin. Yeah, actually, the real story is more complicated, roughly speaking. So, yeah, so Professor Tanaka and his group apply the magnetic field to this particular material and change the temperature and measure the magnetization. And this magnetization is basically determined by how many electron spins are flipped from the original system. And then they found this kind of result. So initially, by lowering the temperature, the magnetization goes down, which is kind of natural because if you increase the temperature, you can flip more spins by thermal fluctuation. But if you cool down the system, you can lower the thermal fluctuation and also number of flip spins. But surprisingly, at least at that time, as you go to lower temperature, actually magnetization somehow increases. So this means that the number of flip spins somehow increased by going to lower temperature. And for these experimentalists, it was kind of mysterious because, yeah, this was consistent with theory at that time, but they didn't expect this upturn at low temperature. But yeah, so existing theory at that time looked like this. And, at low temperature, it was supposed to be very flat, but in reality, they observed upturn. So yeah, so I listened to this seminar and I came up with some idea. Well, it's a long time ago, but anyway. So suppose your original system was like this, and by magnetic field, you flip one of the spins. Then what happens to this flip spin? Then actually, because of the interaction with the neighboring spin, so you can flip this spin and you can go back to the original state like this. So this can continue like this. So this is a flip spin. So originally flip spin was there, but because of the interaction, this guy came back to the original direction and flipped this spin. And next, because of this interaction, you flip this spin and this guy comes back to the original position. Then this means that the flip spin can move around the system. Although the real electrons are localizing each atom, so electrons themselves are not moving, but the status of this flip spin can move around. And so this is like actually like a particle in this case, kind of fictitious particle moving around. So because you can identify this original configuration as a vacuum and this flip spin as a particle, then this particle can move around. So yeah, this location of flip spin can move around in the crystal, and this can be regarded as so-called one of the quasi particles. In this case, called magnon or trichlon. So let's call this magnon. Then, so actually, this magnon can be regarded as a particle, and of course, this is not real particle because it's just a status of flip spin. But if we recall this Tomonaga's explanation, why particles are indistinguishable, then this looks like very much like an electronic signboard. The status change of signboard, we can interpret as a particle. So this is particle in some sense. Then we can show that these magnons obey Bose-Einstein statistics, so they might be bosons. So if you go to very low temperature, sufficiently low temperature, we can expect Bose-Einstein condensation. And actually, we can explain this upturn in terms of Bose-Einstein condensation, because the number of ordinary magnons just decreases as you go to lower temperature. But at certain temperature, you have this Bose-Einstein condensation transition, and below that, the magnons tend to flock to the same state, this Bose-Einstein condensation. So if you include this effect of Bose-Einstein condensation, the total number of magnons increases, then that means that the magnetization actually increases. So this can explain this initially surprising experimental result. So this is my old paper, but still one of my favorites. And yeah, so to summarize, so yeah, we have particles in microscopic world, and often those particles are illustrated as small balls or grains, which is, of course, to some extent correct, but not exactly correct. One reason being in balls we are familiar with, you can always distinguish two balls even when they look very similar. But in microscopic world, identical particles are really indistinguishable. You cannot distinguish even in principle. And one type of such particles is called bosons, obeying the Bose-Einstein statistics. And as a result of these statistics, we can expect Bose-Einstein condensation. So roughly speaking, the bars of the phasor flock together is the Bose particles. And this also has application beyond the conventional particle like magnons. So magnons is one type of quasi-particle in materials. Those are not real particles, just a status change of, let's say, electron spin in the material. But this status change can propagate very much like a particle in the vacuum. And as I emphasized, and also according to Tomonaga, the real particle, according to modern view of quantum field theory, not so much different from those quasi-particles. So yeah, I would say the real particle, quasi-particle, of course they are different, but in essence, maybe they are very similar. Anyway, so even those quasi-particles like magnons, they can also undergo Bose-Einstein condensation, which are consequence of this Bose statistics, which is a consequence of you cannot distinguish two identical particles. So yeah, I had prepared a more modern part, but let me stop here. Thank you for your attention.
Thank you for thought-provoking talk. Questions? Sir.
So I'm having a little bit of trouble reconciling this notion that bosons, generally speaking, when you remove the distinguishability, have statistics that are different than classical systems. So I guess I'm trying to pin down, I think that there are situations where bosons behave classically. So I guess I'm trying to figure out what exactly is the situation where this happens. And then just to give an example so it's more clear of when you get classical statistics from bosons. You take photons and you put them on a beam splitter and you split them into two directions. And there's a 50-50 chance of which direction they go in. And if you repeat the amount of identical bosons that you add, identical photons, you have them go through the same place. That's equivalent to flipping multiple coins, you can think of. And if you collect the statistics of what happens there, it's completely classical. You do not get any sort of special quantum effects, and it behaves just like a binomial distribution.
So maybe I should discuss the detailed setup, but one answer is that, okay, so in this kind of discussion, I assume that these particles or coins really have only two states, head or tail. But of course, for real particles, this particle can occupy different positions in space. And actually, those are different states. So if you consider, the particle in the space, it's much, much more complicated because you can distinguish identical particle located here from located here. Yeah. So maybe your case is related to this, but I have to think about it.
Okay, we can go over it, but I think just single input of a beam splitter, even if you assume there are just two output modes, behavior that's completely classical in terms of the statistics.
Okay. Yeah, maybe we can discuss it later. Yeah, thank you. Yeah. Because yeah, this is very, very simplified. Okay.
Other questions?
So I want to ask the last part about this Magnum condensation. So if you think about these magnons just as this one Magnum dispersions and so on, and at finite temperature it starts to occupy some Magnum, like part of the Magnum bands. Is that the equivalent viewpoint of this condensation, or it's something else?
Yes. So okay. So yeah, I think in many cases you have so-called Magnum band, but the bottom has non-zero energy.
Yeah.
So in that case, if you increase the temperature at high temperature, you have more magnons. So I think even in that case, you can observe this kind of curve. But I think this part is related to the fact that this magnetic field acts like a chemical potential. So this phenomenon is observed only when this Magnum band bottom is tuned or near zero. Yeah. Yeah.
Okay. Yes.
So yeah, we can discuss crossover, but as the bottom of the Magnum band moves away from zero, we don't observe this. So yeah.
Okay. Thank you.
Other questions?
Is the correlation between these particles is a necessary condition for this statistics or not?
For statistics,
yes.
In principle, okay. So maybe it depends on how you define a correlation. So in my view, okay. So in physics, often, especially in condensed matter physics, we often call some system as a strongly correlated system, when there is a so-called particle-particle interaction. Like you put one particle here, another particle near this particle, then there's some repulsive energy due to interaction or something. But even when this kind of interaction is absent and completely free particles, if they are quantum particles obeying the Fermi-Dirac statistics of both Einstein statistics, at least in my definition, they are correlated to some extent, just really because of these statistics. Yeah, for example, in you probably know, so there is another statistics, Fermi-Dirac statistics. In that case, two particles cannot occupy the same state. In that case, if you put one Fermi particle here, then another particle cannot really come to the same position. So this is already some sort of correlation coming from exactly from quantum statistics. So I would say these quantum statistics already implies some sort of correlation between the particles, but often as a technical word, at least in some literature, if there is no interaction, people call this no correlation or something. But yeah, well, it depends on how you define. But this effect I explained mostly can happen without any interaction.
Any further question?
Is
it's about history.
Mhm.
Because he just mentioned fermions.
Mhm.
I'm curious if Professor Tomonaga also mentioned anything about fermions. Picture, because the picture you show is appropriate for only for bosons.
Yeah. You mean this electronic signboard picture? How he discussed fermion? Okay. Well, not explicitly, but as you probably know, this fermions corresponds to excitation in fermionic signboard, where these LEDs obey this anti-commutation relation or something like that, which I don't know how to view that. Yeah, but maybe that's an interesting question. But yeah, I don't have clear answer. Also, Tomonaga didn't discuss that much detail as far as I know.
Okay. Well, we can take away the thought of the algebra of LEDs with us and thank Professor Oshikawa again for a fun talk.